Hello everyone. Welcome to another screencast for contemporary software development at Portland State University. The ability to understand and reuse software written by other people is a key skill for any contemporary software developer. Understanding the patterns and application programming interfaces applied to a development platform, like Java, is essential to build familiarity with the code that you build and extend. In this slide deck, we continue our exploration of the standard Java APIs with a focus on the suite of collection classes that group objects together. As we've seen in other slide decks, Java provides a number of APIs, application programming interfaces, for doing all sorts of great stuff, the kind of stuff that you do in programs, like working with I/O or manipulating strings. The best part of these APIs is that this is code that you didn't have to write yourself. You can use someone else's code and take advantage of years and years and years of testing and optimization. One particular set of APIs that people have found to be very useful are the Java collections. These collections APIs range from just general utility classes that we'll look at to a very deep and robust suite of collection classes that group other objects together in valuable structures, like maps and lists. And as we'll see, the collection APIs benefit greatly from some language features like generics and the enhanced for loop that make it easy to integrate these classes into your own code. So the java.util package contains a lot of classes that are very useful and handy. I use them all the time in my code. We'll talk about a number of them in these slides. We'll start with some of the original, if you will, utility classes like string tokenizer. We'll talk about hash table and stack. Then we'll dive into the full collection class hierarchy. Now, not only are these useful tools for your programs, they're also very good examples of object-oriented programming. Additionally, we'll also talk about system properties of the Java virtual machine. The Java util string tokenizer class is used to parse a string. So you've got a string and you want to find subcomponents of it. Now, some of you might be more familiar with using regex or regular expressions for extracting information out of a string. String tokenizer I like because it's pretty straightforward. It took me a long time to really become familiar with regular expressions, and it's not something that I would expect people to be able to do on day one with a language. String tokenizer is a plain old Java object. It's got a constructor that takes a string, and this is the string to be parsed, and then another string whose characters delimit what are called the tokens. This is basically the pieces, parts of the string that you want to break up. If you don't provide any delimiter characters, by default, it'll just parse based on white space. Once you have one of the string tokenizer objects, you can invoke some methods on it. You can call count tokens, which will return the number of tokens that haven't been extracted yet from that string. You can then call next token to return, well, the next token in the string. You basically go token by token and iterate over it. And then also there's a Boolean method called has more tokens, which returns whether or not there are more tokens to be handled. Here's an example of using string tokenizer. It's a main method that takes two arguments. The first one is the string to be parsed, and then the second argument is the characters that delimit tokens in the string. So pretty straightforward. We create a new tokenizer object with the data that's passed in the command line. And then we have a while loop that says, hey, while there are more tokens for the string tokenizer to parse, get the next token and print it out. So down at the bottom of the slide, you see what happens when we run this program with two arguments. This comma is comma a colon sentence period. And then delimiters of comma and colon. And you'll see that it prints out 4 tokens. This is a sentence. So I like string tokenizer for doing basic parsing of strings, validation of things like dates. Now let's talk about the collection classes. So what collection classes do is they group objects together in interesting ways and provide valuable operations on those grouped together objects. So the very first version of Java contained some collection classes that were very useful. As a matter of fact, at the time, everybody was just overjoyed to have these as part of the standard API because they didn't have to write their own growable list. They didn't have to write their own stack. They didn't have to write their own hash table anymore. They could reuse the ones that the developers of the Java platform had built. So while these classes were very useful and very popular, again at the time, it was a really great selling feature of the Java language. They weren't optimized. They provided the functionality, but they were bulky. They were kind of slow. They did some things that with like thread synchronization that weren't optimal. So in a subsequent release of Java, they introduced the new collection classes hierarchy, and this is what people have been using ever since. The collection classes really provide some nice lessons in abstraction and object-oriented programming, and we'll be highlighting that throughout this slide deck. So when you look at the contents of the Java util package, you'll see there's a lot of classes, a lot of interfaces. And where I like to start is with this set of interfaces for representing collections. So there is a hierarchy of interfaces that is rooted at collection and has sub-interfaces like list and set, and then there is a sub-interface of set called sorted set. And each one of these provides a little bit more functionality, and we'll be looking at them shortly. And then there's something called iterators. Now, iterators abstract, well, iterating over a collection. As you'll see, each collection has different behaviors, and you can't always rely on the order in which objects are stored in a collection. And this is okay, because maybe what all you want to do is just say, hey, just tell me what all of the contents of this collection are. So that's what an iterator is. There's a subclass of iterator called list iterator that we'll talk about also. And then finally, there are maps. These are like hash tables. You got key value pairs. And so there's a map interface and a sub interface of that called sorted map. So let's take a little bit and talk in more detail what these interfaces are all about. Java util collection is a very abstract notion of an object that groups other objects together. It has methods like add, right? You can add some object to a collection. You can say whether or not the collection contains an object. Is there anything in the collection? Is it empty? You can get an iterator over a collection, meaning that this is an object that knows how to visit each element in the collection. You can also remove an object from a collection, and you can get the size of a collection. So all collection objects, all types of collections have these behaviors, and it makes sense, right? You can add something, you can remove something, you can get the size. These are very fundamental concepts in the collection. But note that there are certain properties you can't find, right? You can't ask, hey, what is the seventh element of a collection? Because, well, that isn't defined. Collections don't necessarily have an order. If you want more specific and refined behavior out of your collection, you can use one of the sub-interfaces of collection, like list. So a list is a collection that is indexed. Every element in that collection has an index, a number associated with it, starting with 0. And the list interface will do things like overload the add method to add an object at a given index. You can also get and set the object at a given index. In addition to getting an iterator, the thing that you inherit from collection, you can also get what's called a list iterator that will allow you to, well, go back and forth. We'll see what we'll see what list iterator is all about in a little bit. So list is like when you want to have basically a growable array, right? You can index into it. You can say, hey, give me the 27th element. Java util set is a collection whose elements are unordered, but each element in a set is unique. Meaning that, let's say, you've got a bunch of numbers, and you put a bunch of numbers into just a plain old collection. The same number could appear multiple times. In a set, the contents are guaranteed to be unique, so if you put in the number 23 once, it's not going to get put in there again if you attempt to do it. The way a set determines whether or not it already contains an object is that it uses the equals method. Right? Recall that every object in Java inherits an equals method from JavaLang object. And so therefore, the set can invoke the equals method to say, hey, as I'm looking to see if I already contain this other object, I'll just say whether or not it equals the object that I already contain. So this is where you use things like the equals method, is in the set class. Now, as I said, elements in a Java util set are unordered. If you want a collection whose elements are ordered, you use Java util sorted set. And so, again, this is a set. It's got the same methods as set, plus it adds a couple more, like you can get the first element, and you can get the last element in a set, because, again, they are ordered. And we'll see how they're ordered a little later on. Now, we mentioned that all collections have the ability to obtain an iterator over themselves. And this is an object that is used to, well, iterate, to visit each of the objects in a collection. The iterator interface has some very abstract notions, like it says, hey, do I have another element to deliver, right? Is there another element for me to iterate over? And you can also get the next element. And you can also remove the element that was just returned next. So if you want to modify a collection while you're iterating over it, the best way to do that is to work through the iterator to remove it. This is kind of a rare thing to do, but I think it provides an interesting example of how the developers of this library chose to represent iterating over a collection. An iterator can only iterate over objects in sort of one direction. They sort of start at the quote-unquote beginning and go to the end. You can't go back and forth. A list iterator can, because list iterators are created from lists. And lists inherently have a notion of the order of their objects, the index of their objects. So the list iterator has methods in addition to iterator, like add. So you can add an object to the underlying list that's being iterated over. And you can, in addition to having next and has next, you have previous and has previous. You can iterate both directions over a list. And you can also get the index of the element that would be returned by the call to next or previous. So the map interface represents a mapping of key objects to value objects. And it's like a hash table if you're familiar with that. This is a different kind of collection because it's not just a grouping of singular objects, it's a grouping of pairs of objects. Again, each key object is mapped to a value object. So its API is a little bit different from the collections that we've seen so far. The way you establish a mapping between one object to another is by invoking the put method. And if you remember back to your data structures course, the way you implement putting something into a map or into a hash table, you have these buckets which are lists of particular objects that all have something in common. And usually the bucket associated with a key object in a map is determined by invoking the hashcode method of that object. Again, this is where the hashcode method is used. And recall that every object in Java has a hashcode method, has the ability to say, well, here's what my hashcode is. This is in turn used by an object like a map to then store its data internally. So you create a mapping with put. You can return the value object associated with a given key by using the get method. And then you can ask the map to, hey, do you contain this key? Do you contain this value? It knows how to look these things up internally. Now, when it comes to getting access to lots of objects in the map, there are a couple of methods there. There's a method called keySet, which will return all of the keys in a map as a set. Now, recall that in a map, each key object is unique. If you attempt to make multiple mappings for the same key, the new one will just overwrite the old one. And so as a result, all the keys in a map are unique. And so then the API, when it chooses how it wants to represent the keys, it returns a set, because a set has objects that are all unique. You can also get all the values that are stored in a map. This values, however, are represented as a collection because it's possible that you can have the same object mapped to two different keys in a map. So they're not guaranteed to be unique, or there's no other guarantees about them. All it is a bunch of objects, and when all you've got is a bunch of objects, you represent it as a collection. The entry set method gives you a set of the key value pairs. So when you iterate over the entry set, you actually get this little tuple object, it's called a map.entry, that allows you to say, well, here's a particular key, and here's the value that it's associated with. Again, these methods are useful when you are working with the map. You populate the map, and then when you want to get information out of the map, you use methods like keySet, values, and entry set. So what we just talked about are a bunch of interfaces, right? And interfaces are these very abstract concepts, and all they have is behavior. They don't have any state. You can't instantiate an interface. However, you can use the interface type anywhere in the Java program as a field value, as a return type, as a parameter to a method. Interfaces are really great. But at the end of the day, you'll need to create some objects, and of course, those need to be concrete. So the Java Util API, the Collections API, also contains a bunch of classes that implement these interfaces and provide various implementation of the collections of the data structures that are modeled by the interfaces. If you look at the class hierarchy for the collection classes, at sort of the top are the interfaces, things like collection and set and list. Then there's this layer of abstract classes that implement common functionality for the interfaces. So you'll have like abstract collection, and then you'll have abstract list and abstract set, which are subclasses of that, and then everything implements the appropriate interface. Finally, at the bottom of the hierarchy, you have your concrete implementations of these classes, things like hash set and tree set, which subclass abstract set. Tree set is sorted, so it implements the sorted set interface. Similarly, for lists, you have linked list and you have array list, which we'll see in a moment, but these are implementations of the lists that are implemented in different ways for different reasons. So let's look at some of these concrete classes that implement the collection interfaces. So in Java util, there are several classes that implement the list interface. Remember, list is a collection that is indexed, so you can say, hey, give me the 27th element of this list. There's a class called ArrayList, which provides the list interface, which is backed by an array of objects internally. There's also something called a linked list, which is the list interface, which is backed by a linked list. You can probably recall from your data structures course in which situations you want to use an array and in which situations you'd want to use a linked list. Interestingly enough, the linked list class also provides stack-like behavior, so you can push and pop onto a linked list. The vector class, which has been around since the very first release of Java, was retrofitted to implement the list interface. So this is nice. If you're already using vector in your code, it now implements list, and so this allows you to evolve your code base to start using the more abstract collection interfaces like list, even though the implementation currently uses vector. There's also several implementations of maps. So there's something called a hash map, which is basically a hash table, implements the map interface and provides constant time get and put. If you've got a large map, or if you're worried about the cost of lookup, you can use something called a tree map, which implements the interface. It sorts the keys so that you get log n time get and put. Realistically, I haven't found that it makes too much of a difference in most applications. Sure, there are cases where you definitely want to be able to have this option, and it's nice that Java provides both of them. But there are lots of other problems to work out before the most important thing to focus on is whether or not I should use a tree map or a hash map in my code. There are a couple other implementations of map, like identity hash map and linked hash map, that provide more capabilities internally and just provide different semantics. Most likely, the code that uses these maps will want to program to the interface, will want to just say, hey, I've got a map, it's implemented somehow, doesn't really matter. But then as you as a developer, you need to make a choice of what map implementation you ultimately use. Finally, there are a couple of implementations of set in the Java util package. There's something called a hash set, which is a set that is backed by a hash table. Basically, it uses the hash table to create the set of unique values, because everything that you put into the set is just a key in a hash table. And there's also a tree set, which provides the sorted set interface and backed by a red-black tree data structure, which you may or may not have learned about in your data structures course, but basically it provides a sorted set of objects that are stored in a tree format for effective insertion and querying access. We've talked a lot about these collection classes. Let's see some of them in action. Here is an example that works with collections. So we're going to be using a lot of classes from the Java util package, so we need to import that. And we've got a main method that creates two types of collections and prints them out. Let's take a look first at this print method that prints the contents of a collection. The print method takes a capital C collection object, and the way we print out each element is that we get an iterator. So the first thing we do is we get that iterator object, and then we're going to iterate over it. So as long as the iterator has more objects to visit, I'm going to get that object by invoking iter.next. A collection contains just a bunch of objects, and so whatever I get out of it is an object, and I'll print it out. And this code doesn't really care what the collection contains. So this is pretty straightforward code. Here's what we're doing. But note again that iterator, right? This is if you've ever worked with collections before, like a linked list or some sort of growable array, you're probably used to indexing into it. Well, because there are types of collections like sets in Java that don't have a defined order to their contents, you can't say give me the 27th element. Instead, just like give me the next one, and it's up to the iterator to keep track of what's next. And that's fine, because you don't really care in this case. Now let's look at the main method. The first thing the main method does is it creates a new array list. So as you'll recall, an array list implements the list interface, which is a subinterface of collection. So therefore, an array list is a collection. You can make an assignment of a new array list to that variable C of type collection. And we're going to add some stuff to it. We're going to invoke the add method, which appears on collection. We're going to add 3 strings, 1, 2, and 3, and we're going to print that out. I'll print out a new line. Then we'll create a new hash set from the contents of that collection C. So we pass the collection C into our hash set. That constructor will add the contents of that collection C to the newly created hash set, and we'll assign it to a variable called set of type set. Again, we are reinforcing the fact that the hash set implements the set interface. We could also have typed that to a collection because a hash set is a collection also. And then we add 2 more values to that hash set. We add the string 4 and we add the string 2. And we'll print that out. Now let's look at what happens when we run that program. Remember, we created 2 collections. We printed each one of them out. The first collection that we created was an array list with the strings 1, 2, and 3. When we print that out, we get the strings 1, 2, and 3 printed out. Okay, that makes sense, right? An array list will retain the order in which elements are added to it, and we put in 1, 2, 3, we get out 1, 2, 3. Then we created a hash set. Remember, a hash set is a set, and therefore the elements in the collection are unique, which means that no element will appear more than once in that collection. We created that hash set with the contents of the array list, which was 1, 2, 3. Then we added 2, and then we added 4. And when we print that out, what we see is the strings 1, 3, 4, and 2. And so that's a little interesting. It drives home a couple facts about the hash set. First of all, it drives home the fact that the elements of a hash set are not ordered. So even though they went in 1, 2, and 3 from the array list, it doesn't necessarily mean that when you get it out, you're going to get them out in the same order. Furthermore, we added the string 2 twice, once to the initial collection, and then we added it again to the hash set, and it only appears in there once. So we did a total of 5 adds to that hash set, but there's only 4 elements because 2 was duplicated. But this also demonstrates that your program may or may not care that the underlying collection that you're using retains the order in which things were added or guarantees that things are unique. If you look at that print method, it doesn't care whether or not it gets an array list or a hash set or some other collection. All it knows is it's got a collection, it's going to iterate over it and print it out. And for me, this is the big lesson of this whole class and interface hierarchy that we're dealing with. I call it programming to the interface, meaning that there's some parts of my code where I'm just going to deal with the abstraction. I'm just going to deal with something very high level like a collection. The fact that at runtime another kind of object is passed in, well, that's great, but it's not something that I'm concerned about. And that helps make the code easier to understand, and it means that you can change some parts of your code without having to propagate those changes everywhere. Because, for instance, we could call that print method with another class that implements collection, and it wouldn't need to care. That print method would behave exactly the same. It doesn't need to change, even though we're sending in a different type of input. So as you're working with the collection classes and you look at the API documentation online, you'll notice that they take objects, right? You can store strings, you can store files, other things like that inside these collections. But they do not support methods for adding the primitive types, like an int or a double or a boolean. And in Java, these primitive types are not objects, right? They are a different concept in the language and in the underlying implementation. However, If you want to use things like, integers and doubles, you can use the wrapper classes to then represent these primitive data types as objects. So here's an example where we can use a capital I integer to put the number 4 into an array list, capital D double to put the floating point 5.3 into an array list, and a capital B Boolean also into that same array list. Here again, everybody's happy here because the collection just takes some object and you've given it an integer, you've given it a double. Great, everything just works as you'd expect. Now you might think that this creates a little bit of overhead, and technically it does, but the Java Virtual Machine has gotten very good at working with these kinds of objects, and it knows how to optimize the creation of things and how these things are ultimately handled at runtime. Now, having to type out new integer every time you want to put the number 4 into a collection is kind of a pain, and so then the Java language has this feature called auto-boxing, which will automatically convert primitives to the wrapper objects and back again as you are calling methods or assigning to variables. It'll take care of the casting and the creation for you. So basically, any place you have an assignment, including the equals operator, including invoking a method, casting, all that kind of stuff, is some form of assignment. It all happens automatically. So here's an example of how auto-boxing works. If you call the static value of method of the integer class, that'll return a capital I integer, but you can assign it to a little I integer, and the compiler does the right thing. Similarly, here in this example, using auto-boxing, you can just add a variable of type little I int to a list type. You don't need to create a new integer object around it. Again, the language and the runtime will take care of that for you. Similarly, when you go and ask the list for its 0th element, it'll return a value of type object because it doesn't know what it contains. So you'll need to cast that to capital I integer, but look, you can assign that to little I int. And you could also cast it to little I int, and the right thing would happen. So as we saw in that last example, the collection types only know how to work with objects, type capital O object. And that's not very convenient. There is a facility in the Java language that allows for generic types. And generic types are used all over the collections API to specify the type of object that a collection contains. So you have this language syntax, which is a type and then a less than and greater than, and inside the less than and greater than you have other types. So you can say this is a list of strings. So a list bracket string bracket is a list of strings. And when you instantiate these classes that use generic types, you can provide the type to which the generic type is bound, again in brackets. So when you want to create a new array list of longs, you would say, well, new array list bracket long bracket. What this provides is compile time type checking for that collection. So if I have a list of longs and I attempt to add a string object to it, it won't compile. Because the compiler said, hey, listen, you said that this list should only contain longs. You're trying to add a string. This doesn't seem right. For me, I think this provides a lot of power to the APIs and helps you understand what these collections contain, which makes them easier to work with. Now, generics add some complexity to Java and to the type system. Some of this is very helpful and purposeful, but sometimes it can get kind of confusing also. One of the things that took me a long time to wrap my head around is the fact that an array list of string is not a list of objects. You would think that, wait a second, array list is a list and strings are objects, so how come that isn't assignment compatible? But then I saw this counterexample and it made a lot more sense to me. So let's say I've got a list of strings there in the ls variable, and if I could assign it to a list of objects, LO, the compiler would let me say, well, okay, this is a list of objects. You can add any object to it. And now I can add a new integer object to the list of objects. But if you look at what it really refers to, it's supposed to be a list of strings. So the compiler does not allow you to do that second line, which is the assignment of a list of strings to a list of objects. Now you can have some very complex nested collections. So let's say you have a list of maps, and each one of the maps is a map of a string to a string, et cetera, et cetera. It can get kind of difficult to type and read and reason about. So you ended up, with things like got this, data variable here that has this complex type, this list of map of string of strings on the left, and you had to duplicate all that on the right when you created the array list. So they introduced something into the language called the diamond generic type that will infer all the types that you need when creating the collection from the declaration of the variable on the left, or really whatever on the left of the assignment. So this is nice, it's much easier. It all fits on one line, and if something changes on the left, you don't need to worry about changing it on the right. So you can just say, list of string data equals new array list, and you have the little diamond, and the compiler will take care of it. I want to talk now about iteration and go into some more details. I mentioned this earlier when I talked about the remove method, that the iterators allow you to make changes to the underlying collection. And you might be wondering, well, why is that? It seems a little strange that the iterator has the ability to modify the underlying collection. But let's take a look at some examples that really explain the motivation for that remove method. Let's say that I'm iterating over a collection and I make a change to the underlying collection. Here's an example that does just that. I have a list of strings and I add two values to that, 1 and 2. I then get an iterator over that collection and I start iterating. And so I get, I get a string. If the string that I just got, it has the value of 1, the word 1, then I will add a new string at the beginning of the list at element 0 with the string start. When I run this program, it encounters an exception, something called a concurrent modification exception. So let's see what that's all about. Essentially what I'm doing is I've got one object, the iterator, that is iterating over a collection that I'm changing out from underneath it. And as you can imagine, the iterator might get confused. The iterator object, which is independent of the collection, sort of loses its place if the underlying collection changes. The vast majority of iterator objects are said to be fail fast, meaning that if there's something about the underlying collection changes, let's say its size, then the iterator will throw a concurrent modification exception when you call next or when you call previous on a list iterator, right? It can't keep track of it. It loses its place. It gets confused and like, something's gone wrong. I don't know if I'm returning you the right result or not. So instead it throws an exception. This is why iterators have a remove method. So if you do want to make a change to the underlying collection while you are iterating over it, you need to work through the iterator so that the iterator doesn't get confused. And so the iterator can then coordinate with the underlying collection. This is actually a nice feature of iteration. It means that you find out immediately when they're out of date instead of potentially returning the wrong results and making a decision based on incorrect data. However, if you read the documentation, not every iterator guarantees that it's fail fast. It might be fail never, which maybe is not what you want. If you're going to make a change to a collection while you're iterating over it, there's probably a better way to do it. Either work through the iterator or maybe iterate over it in a different way. If you've got a list, maybe have like a for loop instead, and then you'll have the right bookkeeping to make sure that if you add an element to it, that your index for the for loop is still the right value. The for loop in Java has the format that we've all come to expect from a C-based language. So the for int I equals 0, while I is less than the size of the thing we're iterating over I++. That format definitely supports. The for loop also has what's called an enhanced syntax that can be used to iterate over arrays and collections. Actually, it's anything that implements the iterable interface, but for these examples, it'll just be collections. So we can say for object O, and then colon or in a collection, go ahead and do it. What this is syntactic sugar over getting an iterator from that collection and iterating over it. This is nice because it not only saves some typing, but you don't need to worry about the iterator object. But it means that you also can't reference the iterator object, which is fine, I would say 98% of the time. The only time you really need that iterator object is when you want to do something like remove from it, which again is a very rare operation. So I find myself using the enhanced for loop quite a bit whenever I want to iterate over a collection. Finally, let's take a look at working with maps. So again, maps maintain a mapping between a key object and a value object. And maps are generified to be able to specify the specific type of the keys and a specific type of the values. So at the beginning of this farm class, we have a print method that will print out the context of a map that associates a string and an animal. We're going to iterate over what's called the key set, which is, well, all of the names, all the strings that are the keys in the map. And so then we say for each string key in the map's key set, we will then invoke the get method of map to get the animal associated with that key. And then we'll print out a little string that says, key plus and a little arrow to the value, which is the animal. And then in the main method, we're going to construct a map of strings to animals. It'll be a hash map. And we'll put in it values like Old MacDonald, Bossy, Clyde, and Louise, because we have a duck called Louise. Again, human, cow, sheep, and duck are all subclasses of animal, but that print method doesn't care. All it knows is that it takes a map of strings to animals. When we run this class, here's what we get. We get Clyde, Bossy, Old MacDonald, and Louise all printed out. There's some interesting things to note here. With hash maps, the order in which elements are iterated over has nothing to do with the order in which they were added to the map. Again, hash maps don't maintain anything about the order of the key value pairs. And this is okay, right? Do you really care what order they're in? No. If you don't, then let hash map do its thing. The keys of this map were strings. String has implementation of hash code and of equals that allow it to be used as keys in a hash table. Ultimately, the hash maps implementation invoked hash code and equals to figure out what bucket the key value pairs ultimately are stored in. So this means if you're going to use a class that you write as a key into a map, you'll need to override equals and hash code such that their semantics are appropriate to a map. Meaning that if you have two instances of your class that are logically equal, the equals method will return true for them, and those two objects will have the same hash code. So, okay, I think this is a good stopping point. We've seen a lot already. We've seen some fundamental utility classes like string tokenizer, and we've seen components of the collections API like lists and maps. We also saw how language features like autoboxing and generics enhance the collection classes and make them easier to use. We also saw how iterators provide a flexible abstraction over visiting each element of a collection. However, there's still a lot more to explore. I encourage you to continue on to the screencast for part 2 of our exploration of Java collections, and in that screencast we'll discuss comparing objects and sorting collections, type-safe enumerations, and system properties. I hope that all this material gives you a solid introduction to how you can leverage Java's collection classes in your own work in contemporary software development here at Portland State University.